the amazing party that we had last night. So let's start with the session, the mathematics of machine learning. So the first speaker on this session is Pablo Barceló. Pablo is a full professor at the Pontificia Universidad Católica de Chile, where he also acts as the director of the Institute of Mathematical and Computational Engineering, and he's a principal researcher at both the Millennium Institute for Foundational Research on Data and the National Center for Artificial Intelligence. His areas of research are database theory, logic, in computer science, and the emerging relationship between these areas and machine learning. Thank you so much, Pablo, for being here.
Thanks, Soledad. Thanks, Soledad, for the invitation. And yes, thank you for being here so early in the morning after the party. Well, I'm going to talk foundations of interpretability, mathematical foundations of interpretability. And this work is placed on the area that people have started calling formal explainable AI. Yeah? So the literature has started to claim that reliable explainable AI is a prerequisite for trustworthy AI. Yeah? And then our work is framed in the context of this formal explainable AI, which is explainable AI with mathematical guarantees. That's the idea. Yeah? So what is the explainability problem that we will be looking at? The explainability problem is the following. You are given a Boolean machine learning model. The assumption that it's Boolean is not essential to many of these results, but it's much simpler to frame the problem in this context. We're given a Boolean machine learning model that takes as input n features that are between 0 and 1, and outputs also a Boolean value. Yeah? And the question is, how can we explain on a given input, the output of the model? Why the model is given this output on this particular input? Yeah? That's the explainability problem that we will be studying. So people have, of course, you have different Boolean machine learning models like decision trees, linear models like perceptrons, binary decision diagrams, which are extensions of decision trees, Boolean circuits, neural networks, or multi-layer perceptrons, and so on. And people have claimed different levels of interpretability for these models. So for instance, people in general say that linear models, decision trees, or BDDs are either easy to explain or self-explainable. Yeah? Decision trees in particular, people say that it's a self-explainable Boolean model. And on the other hand, of course, neural networks and some classes of Boolean circuits are hard to explain. Yeah? And what we wanted to do in the beginning is try to understand what is the correlation between these folklore claims and the computational complexity of these problems. That's where we started. Yeah? So I'll try to define some metrics and some scores that people have used to provide explanations, and then try to understand the computational complexity of these problems over different architectures. Soledad, can you tell me when I have 10 minutes left? Yeah, so. Okay, so what are the kind of queries and scores that people have looked into? There are things like minimum change required, right? This talks about the robustness of the output of the model with respect to the input. Like, the question is, how many of the features of the input I have to flip in order to change the output? That is minimum change required. There are also minimum sufficient reasons. So given this input, what is the minimum, or in some cases minimal, subset of the features that fully explain the output? That is, if I keep these features and I change the others in any way, the output of the model keeps being the same. Yeah? This can be seen, this minimal subset of or minimum subset of features can be seen then as an explanation for the output of the model. And people have looked also into game theoretical concepts like the Shapley score, yeah? the Shapley value of this set of features seen as a set of players. Yeah? So let me talk a bit more formally about these explainability queries. I'll be not talking about the Shapley score here. I think that Jeremias will talk a bit about it. Will you? No, sorry. Yeah, he will not. I will not be talking about that. I'll focus on minimum change required and minimum sufficient reason mostly. So minimum change required. What is the minimum number of features we need to flip in E in order to change the output? Yeah? So this paper can be accepted if the introduction is written properly and the mathematical content is polished, right? That's what you have to change in order for this paper to be accepted. Or a minimum sufficient reason, right? What is the minimum subset of the features that suffice to obtain the output? Regardless of the content of this paper, it was rejected because it exceeds 10 pages and uses font 10pt, right? I don't care about the mathematical content of this paper. It was going to be rejected no matter what, right? You can formally define these things, but I'm sure that you already understand the idea. I'll not get into detail. I can provide an example with a Boolean model, right? For instance, if we have a Boolean model, there is the disjunction of two features, x1 and x2, and we have an instance that assigns a 1 to both, then the minimum change required in this case is 2, right? I need to flip both inputs in order to change the output. And then what is a sufficient reason? A sufficient reason is a subset of the features such that the output of the model on this input is invariant to the features that are outside the sufficient reason. People call them also prime implicants. Yeah? Okay, so the first thing that we tried to do was to understand the correlation between these claims and the computational complexity of these problems. So we did a table. We studied the computational complexity of these problems for different models. Yeah? And what it appears there? For perceptrons, perceptrons are in fact explainable under this view based on computational complexity. All these problems can be solved efficiently, that is, in polynomial time for this model. But for decision trees, we have something that was quite surprising for us. That is, although minimum change required and minimal sufficient reason can be solved efficiently, the problem of finding a minimum sufficient reason over a decision tree is NP complete. Yeah? So typical metrics for evaluating, for computing an explanation of a decision tree, which would be a minimum sufficient reason, take essentially exponential time to compute. Yeah? And on the other hand, for neural networks, things are just difficult, right? Even the minimum change required is NP complete. The other one belongs to what we call the second level of the Boolean hierarchy. It is like you need even more time to compute it. Yeah? So,
what is the complexity with that? Is it the input size or is it the model?
it's the model with the input size. Typically, the input size, I mean, because the input size is included in the model, right? Because it's, for instance, the number of features of the decision tree. So it's the model, yeah.
What is the minimum sufficient reason for a neural network? Is it in terms of the gradient of the things we have?
No. I mean, if you see the definition of minimum sufficient reason, it's model agnostic, right? It just depends on the input, right? So it's like, what is the minimum subset of the features such that the output of the model will be completely invariant to this? So it's model agnostic, all these definitions, right? SHAP score as well. Okay, some models, decision trees, are more interpretable than neural networks for all queries in terms of computational complexity. Decision trees, however, are not so much interpretable in terms of minimum sufficient reason, again in terms of computational complexity, and perceptrons present good interpretability properties in general. Yeah? Now, in the 8 minutes that I have left, I want to present a bit about these symbolic languages that I was talking in the beginning. So I'll just present the introduction to this. I think it will be clear enough from this. I'll present the basic idea. There are many interpretability queries, right? So you can come with your own interpretability queries. Yeah? So we studied the computational complexity. We tried to understand the correlation with folklore claims. But what if new queries come into the picture? We will have to study this again and again. And several communities in computer science, in theoretical computer science, have handled these kind of problems, right? So if you think about databases, for instance, people do not study this query, this query. They develop declarative query languages, right? So that you can specify your own query. And declarative query languages in general, but for explainability in particular, would have several benefits. You would allow more flexibility to users for writing their own queries. You would provide a clear syntax and semantics for such queries. In many cases, there are scores or queries that do not have a clear semantics, right? But with a query language, you would have this. You would make explainability tools more accessible for practitioners, right? Typically, a declarative query language is much simpler to implement. I mean, it's easier to write something in SQL than writing your code to run that query. Yeah? And it would open a path for optimization of explainability tasks. Okay, so this part will look a bit scary, but it's not. What is it that we try to do? We try to do any Boolean model, and this again is model agnostic, right? So it doesn't depend on the internals of the model, as a logical structure. This logical structure is of exponential size on the original model, but the idea is not to construct it. The idea is to reason about this on the fly somehow. Yeah? So the structure contains tuples of zeros and ones, and this bottom, that is the undefined value. Yeah? And we will have two predicates, a binary predicate that is called completion, and a unary predicate that is called positive. So the domain are all these n-ary tuples of zeros, ones, and undefined values. The binary predicate completion tells me when a tuple is more complete than another one. So for instance, the tuple 1, 0, bottom is more complete than 1, bottom, bottom, because I obtained this one by replacing this bottom by 0. Yeah? So this defines a partial order on the set of partial instances. And finally, the unary predicate, positive, is interpreted as the set of positive instances, right? Those instances that are composed of zeros and ones only, and that are classified positively by the model. So what we studied is just first order logic over this interpretation. Yeah? And then you can start defining interesting things. First of all, our objective here is not to have a practical query language, but to have a lean, simple language that can be theoretically studied and can serve as the basis over which practical languages can be constructed. And we're trying to go in that direction, in fact, these days. Yeah? So for instance, what can you say? I can define the set of full instances, right? What are full instances? Full instances are those instances without bottoms. How do you define them in the logic? Are those instances X such that any completion set of X is equal to X, right? There are no different completions. Yeah? So now I can define when y is a full completion of x. I can say that y is a completion of x and y is full. Yeah? I can define the pairs of same class full instances, right? I can say that both x and y are full, and one is positive if and only if the other one is positive. Yeah? And with these basic things, then you can start defining more refined things. So for instance, I can define the binary predicate sufficient reason. So when x, the partial instance x, is a sufficient reason for y. Well, first of all, y is a full completion of x. Yeah? And second, any full completion of x belongs to the same class than z. Yeah? That's the idea. Sorry, belongs to the same class than y. Yeah? Any full completion, so it doesn't matter how I complete this partial instance x, it will give me the same result than for y. Yeah? And then I can define minimal sufficient reason, for instance. Minimal sufficient reason means it's a sufficient reason that doesn't have inside another smaller sufficient reason. And I can say that, right? So y is a sufficient reason, sorry, x is a sufficient reason of y, and any set that is also a sufficient reason for y, and set is contained in x, equals x. There is no smaller one, right? So this is a very basic logic, but still it allows you to express interesting things, and that's what we wanted. Now, how much time do I have? 5 minutes? Okay. Okay. What else could you express? We could express properties about bias detection, for instance, right? Imagine that you have a model of dimension n and you have a set P of protected features. Yeah? So we say that an instance is biased, and I think that there is a mistake here. Yeah, there is a mistake. It should be P, not in P. So an instance is biased if there is another instance E prime that coincides with E in all non-protected features, and yet the output of the model differs on them, right? You're using the protected features somehow to decide, to classify the instance. So with some more or less complicated queries in the language, and with the use of constants, and this is important, you can use constants in this language, we can express this, right? So we can define first a predicate match that tells us when x and y take the same values on non-protected features. It should be non-protected features here again. Yeah? So it tells us when two instances x and y are equal for these non-protected features. And then we can say, for instance, that x and y are a witness for the model being biased by saying they're both full, they match, that is, they have the same value on non-protected features, and yet they differ on the output. Yeah? And then we can say, for instance, that the model is biased by saying that there exist these witnesses to the model being biased. Yeah? Now, you could express more things, right? If you add more expressive power to the language, right? For instance, if you add counting features to the logic, counting functionalities, you could express minimum change required, which is not expressible. You could express sharp score if you add aggregation and so on. Yeah? But our idea was to have this core language to be able to study. And what we did, among other things, was to study what is the computational cost of evaluating this language over decision trees, basically. Why? Because decision trees are claimed to be very easy to explain, and we wanted to understand what happened over them. And to our surprise, there is a query in this very basic language that it's NP complete. NP hard is actually NP hard, not NP complete. It's NP hard even over decision trees. And it's a very basic formula, right? So what we did, typical things, we try to find fragments of the language that can be evaluated efficiently, or we try to restrict the shape of the models, right? The decision tree has bounded width, for instance, then you can evaluate in polynomial time and so on. Yeah? But that's the idea. I think that it was more important to show you what's the idea behind this language than the specific results. And we can stop with that if you want. Yeah.
Thanks, Pablo. Do we have questions from the audience? Yes.
Thanks for a very interesting talk. Is something known about the complexity of approximating, not finding, say, the minimal sufficient reason, but something that is certified to be a certain percentage? And another question is, what happens if you have no quantifiers, no quantifier alternation? Is that in P?
If you have no quantifier alternation, then it's in polynomial time. So if you have a bunch of existential quantifiers, but then the logic becomes very non-expressive, yeah? So it's very delicate what is the balance between these two things. Now, with respect to the other question, in general, it's also difficult to approximate. And people have also looked into probabilistic minimum sufficient reason. So instead of asking for a minimum sufficient reason that every completion satisfies the model, you could say 90% of the completion satisfy the model. And surprisingly, that problem becomes even more difficult than the yeah. So in general, there are things that are easy to compute under the non-probabilistic approach. And when you move to the probabilistic approach, say you move from delta equals 1 to delta smaller than 1, then they become NP hard. Yeah.
Thank you.
Yeah. So it's curious because when people talk about the explainability of decision trees, they're thinking that the explanation of a decision tree is a branch, right? So the branch will be the explanation to the output. But the problem is that these things are minimum sufficient reason, are reasoning globally about the decision tree, and that complicates the analysis, right?
I have a question. So you had the notion of bias. What is the intuition behind the notion of bias?
No, we were just, it is just a toy example, right?
Okay.
We were trying to give it, we were not claiming anything practical about that. We just wanted to show that you can reason about subset of pictures that you call protected.
Okay.
Yeah.
Do we have more questions from the audience? So at the end of the last talk, there's going to be a joint Q&A if you want to ask more general questions about what kind of mathematical questions are interesting in machine learning. But now we thank you, and then we ask you to come back. Yeah. Thanks. Okay. So the next speaker who's coming to the stage is Jeremías Ulam. He received his degree in bioengineering at Universidad Nacional de Entre Ríos in Argentina in 2013, and then his PhD in computer science from the Technion in Israel. In 2008, he joined the biomedical engineering department at Johns Hopkins University as an assistant professor, and he recently received a very prestigious award from the National Science Foundation in the United States. So thank you, Jeremías.
Thank you, Sole. All right, good morning, buen dia. Thanks again for being here. It's really cool to see everybody. And also extremely thankful to the organizers for putting this together. It's really an amazing meeting. So I'm here to tell you a little bit about trying to understand neural networks. I'm sorry, Pablo, maybe we should have talked before and we could have scheduled and I could have talked about Shapley values as well. But instead, I want to tell you about a class of functions that we call sparse local Lipschitz functions and give you a demonstration on how we can start analyzing these networks by means of these tools. So I don't think I need too much of an introduction as to the importance of understanding these models. The impact that AI tools are having in society continues to increase. Mass media reflects on this. All kinds of general mass audience journals write about this, including Spotify podcasts that my parents sent me a couple of days ago because they wanted to double check something that was said there. Now, it's also important to understand that because these tools are very advancing at a very rapid pace, they have important limitations that we need to keep in mind. This screenshot here is a screenshot of the website of a hearing committee of the House of Representatives in the United States. And this is a hearing committee that took place this Wednesday as I was flying here. And it's a hearing committee on basically some of the risks of deploying some of these tools in society, in real world communities. And it's very interesting. I suggest you look at it if you're interested in these aspects. There's a series of invited speakers and people that the hearing committee interviews, including Alexander Madry and many others. It's a very interesting session. So everybody in this conference has been talking about some of these limitations. Pablo just talked about transparency and interpretability, which is also something that I'm particularly very interested in. There are issues of demographic fairness, issues of optimization, generalization, robustness, and many others. But I will be focusing on robustness and generalization today. And even though these are very different problems, what I hope to convey is the key message that these deep ReLU networks have a lot of structure that we often don't exploit. And by making use of this structure that comes in terms of sparsity, we can refine a lot of the analysis that exists for neural networks. Okay, so diving into the issue of adversarial robustness, I again presume most of the people here are familiar with this phenomenon. These models are extremely brittle and it's very easy to perturb their inputs so that the outputs are very drastically perturbed. And this is not just a digital game. These things can have real-life consequences. This is a very interesting work where these authors basically 3D printed a turtle that when looked at by a computer vision system, it's just recognized as a rifle. And so here you see different views of the actual turtle that's being recognized as a weapon. So I'm sure you can understand the implications of this. This is also a fun work by Tom Goldstein from the University of Maryland. They call this the invisibility clock because when you wear it, basically software that tries to identify people in a crowd just does not see you. And so you can walk around a room and these person identification systems will just not pick up on you. So these are real physical threats, and there's a lot of importance in trying to understand these. So slightly more formally, what do we mean when we say robustness? So for this talk, what I will mean is that I have a function, a predictor. You can imagine this as receiving an input image and outputting a class. And what I want is the function not to change its label, its predicted label, when I add a small perturbation v, and v is bounded, it's small. For the purpose of today's talk, let's just assume that's bounded in L2 norm. Great, what functions are we going to consider? I'm going to focus on functions that are linear maps acting on some representation function, on some feature map. And this feature map can be nonlinear, can be very complex, can be data-driven, data-dependent. And so most of what I will describe applies to these class of functions. And as you can imagine, this includes neural networks as a specific case, but many other functions as well, including kernel methods and others. Okay, so we want to understand robustness of these functions. A very natural starting point is to ask questions of Lipschitzness. the Lipschitz constant of the function simply measures by how much I can expect my function to blow up when I perturb the input. This is very natural, but echoing what Rachel was describing, the intuition that she was depicting yesterday, this is a global quantity. I'm requiring this for any x and y on my input space, and if phi, this representation map, is nonlinear, well, you can expect this to be very, very coarse and just too loose to give us anything useful. And so what we're going to do is refine this notion of global Lipschitzness to what we call sparse local Lipschitzness. And this is different, as you can imagine, in two aspects. There's a local aspect and there's a sparsity aspect. So what we define is that this function will be sparse local Lipschitz at a point x if there exists a set I of inactive indices. So I'm looking at x, and I look at the function computed from x, and some of its entries are 0. And what I require is two things. I require that if I look around a neighborhood around x, the function behaves like a Lipschitz function. And I also require that that inactive set to remain inactive. But importantly, this Lipschitz now, it's no longer a constant, this is a function now, depends obviously on x, because it's a local quantity, but also depends on s, on the number of zeros that I have in my representation map. And as you will see shortly, this parameter s is a completely tunable knob. I'm going to make no assumptions whatsoever about feasible values for s. The user is allowed to tune it so as to optimize the bounds that we will obtain. And as you can imagine, if s goes to 0, I'm requiring no sparsity whatsoever. This radius will grow to infinity, and I'm just recovering typical notions of Lipschitzness. As I require higher degrees of sparsity, then I should shrink my radius so that these inactive sets remain inactive. So this interpolates between traditional notions of Lipschitzness and these more constrained notions. Okay, so why is this useful? This is useful because these allow very, very easy to derive robustness certificates. So, for example, you can show that the label is not changed. Here I'm using Rmax because basically f computes a vector and I'm picking the class corresponding to a certain entry. So the class is not changed as long as the perturbation is no greater than a certain amount. And these amounts depends on two things. Depends on this local radius, local sparse radius, and a notion of margin in feature space divided by the local Lipschitz function. And this makes a lot of sense because what we are saying is that I can no longer guarantee robustness when either of two things happen. Either my feature map is no longer Lipschitz locally, or the perturbation is just too large in feature space to violate the margin. But the key here is that all of these quantities depend on S, and this holds uniformly over S, so I can literally optimize this over the best possible choice of S. And so given a sample X, I can sweep through the value of S so as to obtain the larger certified radius. So this is still a little bit abstract. Let's look at an example. And the sort of canonical example is deep networks, but again, this is a very broad family of functions. There are other very interesting predictors that satisfy these definitions too. Supervised dictionary learning, supervised sparse coding is also a particular class of this. Methods that use dimensionality reduction are also a particular class of this. Okay, so you have a function. Now the function is a linear map on some representation function, and the representation is just a concatenation of affine linear maps and ReLU, stressing ReLU, nonlinear functions. So it's not easy, it's not hard to show that if you take one of these layers, each layer is a sparse local Lipschitz function. And this is very easy to see because what I can do is I can take all of the pre-activations, all of the values that are immediately before the ReLU, and I can sort them in decreasing order. The ones that are above 0 are going to be active. The ones that are below 0 are going to be inactive. So here's what I can do. Let's say that I want S to be 40. Great. I pick the 40 most inactive neurons. And that gives me my value of R. In other words, as long as the input is not perturbed by this amount r, all of these neurons will remain inactive. Why is this good? Well, this is good because if you look at the corresponding Lipschitz function, this is simply the operator norm, but not of the entire matrix, but rather of a matrix restricted to the complement of this set. So restricted to the neurons that are active and those that might become active, the ones between let's say 30 and 60, those might become active. That's okay, I'm going to include them. But nonetheless, I'm computing operator norms of reduced matrices. Okay, and great, if one of these maps is sparse-Local-Lipschitz, turns out that the composition of sparse-Local-Lipschitz functions is also sparse-Local-Lipschitz, and you can have expressions for the corresponding sparse-Local radii, and Lipschitz functions. Okay, so this is all good and nice, but probably you're asking, okay, great, but how sparse are neural networks really? How much is this going to give you? Perhaps there's more sparsity than what you would anticipate, at least more sparsity than what I was anticipating. So here's a 3-layer neural network, 2 hidden layers. Each layer has 500 neurons. And this is on MNIST. All the examples that I'm going to show are very basic and toy-like. I have 500 neurons in each, and what you're looking is a histogram of the number of active neurons at any given point in the input. And you see that, for example, for the first layer, no input activates more than half of the 500 neurons. On the second layer, it's even fewer of them. Now, this doesn't mean that, naturally, that all of the inputs activate the same subset. That would be extremely redundant. All of the subsets are different, but at no given point, all of the neurons are active. It's even more interesting to see what happens when you change the width. So if I repeat this experiment, but now I train models of increasing width, and here the diagonal line denotes just the identity and increasing width. If you look at the number of neurons that are active, it grows very slowly as you increase width. This for the first layer and the second layer also grows linearly, but at a slower rate. So it seems like there's a lot of sparsity. Now we have these tools of sparse-Local-Lipschitz to understand these things. So we can go and compute security curves. And security curves are basically a form of computing certificates. What we are doing is understanding the certified accuracy, so the amount of points that I can correctly predict while being able to certify, as a function of the adversarial radius, as a function of the perturbation strength. And in black, you see the kind of certified accuracy that you would get if you were using just the global Lipschitz constant of the network. And you see that it decreases very fast, and this is because L is huge, and so this is a very coarse sensibility quantification. In red, you see how the accuracy deteriorates as you corrupt the model. So the red gives us an upper bound to the optimal certified radius, which we cannot compute because it's NP-hard. So somewhere in between, it's where we should be. And what you see in green, I apologize, the label here is too small. The green is the one that results from our analysis of using sparse-Local-Lipschitz. This is for a model that's not regularized. This is a model that is regularized, where you are explicitly controlling for the Lipschitz constant of the function. And you see that in this case, the amount of points that you can certify is larger and always better than if you were doing a global Lipschitz analysis. The other methods are 2 other popular methods that are used for certification. I can comment on more of that later if there's time. This is also very fast to compute and very efficient. Okay, so in the last 5 minutes or 8 minutes that I have, I want to give you a snapshot of something else that you could do with these kind of tools. And it has to do with generalization. So in machine learning, we're not just using any kinds of inputs. We're using inputs that we typically assume draw an IID from some distribution. And we minimize, we end up solving an optimization problem because we hope that in minimizing this empirical risk, we are actually minimizing the true risk, the true expected value of the loss. And so what I want to understand is how far are these two things? Hopefully this delta, this generalization gap is small, and therefore my training error will be a good approximation for my generalization error, for my true risk. This is a very open problem in deep learning. There's a very rich literature on statistical learning theory and generalization bounds for deep learning. Perhaps most of the most interesting ones, to my understanding, are those that rely on Rademacher complexity analysis, but more so even the ones that rely on notions of stability of your predictor and flatness of the loss function. However, by and large, the vast majority of all these results, despite being very beautiful results, they're still vacuous. And by that I mean they're huge. They're orders of magnitude above what you would expect from a bound on this delta quantity, because this is a probability. And so this should be between 0 and 1. And these things are order of magnitude larger. And so it's a big part of the statement, we don't understand deep learning. The generalization bounds remain to be poorly understood. So what I'll show you is a way of using these tools to provide some results on generalization that they're not the ultimate answer, but nonetheless I do think have some interesting merit to them. So here's what we can do. For any given matrix W of size D2 by D1, I can define these norms that we call sparse norms. And these are sparse norms because what I do is I look at W and I look at a subset of the rows and a subset of the columns, and then I compute the operator norms of these. And by now, you probably understand the rationale behind this. Every single point in a network activates only a subset of the rows and subset of the columns, and therefore, what I should be really getting a handle on are the operator norms of these reduced matrices. Okay, with these norms, I can construct neighborhoods in function space. So for example, F tilde, which is a neural network, will be in a ball centered at another neural network F of radius epsilon. Epsilon is a vector. If all of the corresponding weights are in a ball in this norm. Okay, it turns out that neural networks are not only sparse local Lipschitz with respect to their inputs, but they're also sparse local Lipschitz functions as function of their parameters. And so you can look at all functions in a neighborhood of another, and as long as the sparse local radius, the same one basically that I described before, as long as that radius is enough, and remember what this means is as long as there's a subset of the neurons that are strongly inactive, then you can obtain bounds on the layer-wise activations and eventually on the output of the model that are tighter than if you were just looking at, for example, the product of operator norms. Great. So with that very, very short introduction on generalization, this is a result that we have. You can bound the probability of misclassification, the risk, by 3 terms. The first term measures an empirical risk, but in terms of a specific margin risk that is up there. It's nothing too peculiar. It's just misclassification up to a leeway of an extra margin. The second term is a sparse loss. And what this is doing is saying, out of my samples in my training set, how many of those samples satisfy this notion of having enough radius? If at any point some of the radii are not satisfied, they then penalize one. Again, this depends on my choice of S. And then there is a notion that depends on the KL divergence between a prior and a posterior distribution. The prior can be anything, as long as it's independent of the data. The posterior is a Gaussian distribution centered at your obtained predictor. So this comes from a pack base bound, but if you notice, it's a de-randomized pack base bound because the bound holds for the deterministic predictor that you obtained. And so this shows a couple of very interesting things. First, this KL term scales as the sum of these reduced operator norms, not the product of them. And so this doesn't scale exponentially with depth, which is a big limitation in a lot of the other bounds. Moreover, there are some very nice trade-offs for sparsity. The larger the sparsity is, the reduced these norms will be. That's great. but the sparse loss will be higher. There are also implications of what the margin risk is, but that's a little bit subtle, and I can comment on that further if you want. Okay, so this gives us bound. S here, S is a knob that I can tune to whatever predictor I have, and you're really free to exploit as much sparsity as you obtain for your model. So what you're seeing here is, again, a distribution of the degree of sparsity on different models of increasing width. This is plotting the number of zeros that you obtain, and again, as I mentioned before, the larger the model, the more zeros you obtain. This is good news. On the right, you're seeing the actual generalization bounds, the quantity that I have on the right, for a two-layer model, which arguably it's a toy model, but you obtained bounds that are pretty good. They're about twice as the value of the true risk. We have further examples on deeper models. You still get non-vacuous bounds. They're a bit looser, and we understand to some extent why this is, but we think this is interesting. Okay, so just to conclude, I hope I convinced you that there's a lot of structure that we often disregard on these networks. If you exploit this structure via these constructions of sparse local Lipschitz functions, you can make a lot of the analysis that already exist a lot tighter. This is work by my brilliant PhD student, Ramchandra Muthukumar, and there are some references here on the things that I described. Thank you.
Thank you, Jeremias. Questions? Yes. There.
Hi, thank you for the talk. Can you extend your results using Helder functions instead of Lipschitz?
Using what?
Helder functions.
Helper?
Helder.
Holder.
Helder, yeah.
Using Holder functions for?
Instead of Lipschitz.
You could. You totally could. I'm not saying this is the best way to quantify sensibility. You could use other notions as well. The entire, the only thing that you need to make sure goes through is that the moment you restrict these things to subsets, there's a combinatorially many of those subsets, that this is still manageable. For this case, it is a case. For a Holder, it should be, but I think it should be checked.
Okay, thank you.
Do you have the clicker? There.
Okay, so the last speaker for this session is Luana Ruiz. She's an incoming assistant professor in the Department of Applied Mathematics and Statistics at Johns Hopkins University, and she's currently a postdoctoral fellow at MIT. She received her PhD in electrical engineering from the University of Pennsylvania in 2022, and she was selected as an MIT Rising Star in EEC in 2021 and a Simons Research Fellow in 2022. So thank you, Luana, for coming to Uruguay, and looking forward to your talk.
Thank you for the introduction, and thank you for the invitation. And thank you guys for being here.
So today I'm going to talk about machine learning on large-scale graphs using graph neural networks, and focusing specifically on the transferability property that Alejandro talked about on Tuesday. But since this is a session on the mathematics of machine learning, what I thought I would do is I would go a bit more into the detail of the theoretical results and some of the key ideas behind them, because I think they're very nice and easy to visualize. So, by this point in the conference and after the two great talks on graph neural networks on Tuesday, I probably don't need to convince you that doing machine learning on large-scale graphs is important. And the reason why it's important is because the need to process information on very large graphs arises in a wide range of applications, right? So two of them are exemplified here on the slide, for example. One is, for instance, product recommendation on product similarity graphs, such as the one that we saw on the practical on Tuesday. Another one is, for example, imagine that you have a multi-agent system that has some limited communications, a limited communication structure defined by a graph in space, and that you want to control in a decentralized manner. This is also an example of a problem where you might want to process information on a very large graph, potentially using machine learning. And in both of these problems and in many problems on large networks, machine learning is typically the solution of choice. And when I say machine learning, what I actually mean are neural networks, right? Because there's an ample amount of empirical and theoretical evidence to support using them for doing machine learning in general and in particular on graphs. But when I say neural networks, what I mean are really convolutional neural networks, which we know scale well to large data because their parametrization is independent of the data size. So these let me just check if I can get this to stop. So these graph neural networks, they achieve great performance in practice, but the graphs on which they seem to work best are graphs of moderate size. So for example, when these product similarity networks and recommendation systems have in the order of a few thousand products, or when these multi-agent systems have in the order of some tens of agents, right? But when these graphs scale, they become much harder to train. And so two important questions that I care about and that I tried to answer with my research were, first, we have empirically observed that GNNs scale well in practice, but we don't necessarily know what are the theoretical reasons why they do. And so this is the first question. And then the second question, following from the understanding that we may develop from the first, is, can this success of GNNs that they exhibit in moderate-sized graphs, can we then leverage the success to generate success at a large scale, right? And I'll be more clear about this point in a few minutes when I talk about transferability. So to answer both of these questions, the approach that I've taken, and I think it's the approach that you should take, is to turn to graph limits. Because limits, they review the intrinsic dimensionality of the data, which is often much smaller than the data dimension itself. And because if we can learn something by characterizing convergence of graphs and of information processing architectures defined on these graphs to this limit, then this can potentially be exploited to facilitate the training of graph neural networks for these large-scale graphs. And fortunately, graphs do indeed have limits that effectively limit their dimensionality. One such limit are graphons. However, this is a solution, but also a challenge, because the existence of this limit doesn't necessarily mean that information processing architectures defined on these graphs converge to limits on graphons, because graphs don't have the Euclidean structure that time and image signals have in the limit. And so these results are not a given, and they're results that still need to be established. Okay, so before I start talking about convergence of graph convolutions and graph neural networks to graphon convolutions and graphon neural networks, let me recap something that Alejandro talked about on Friday, which is the definition of a graph convolution, right? So if we represent graphs as by the adjacency matrix S, and if we represent data on these graphs by vectors X, where each element of the vector represents the data each individual node. We can write the graph convolution as a polynomial on the adjacency matrix applied to the data x. And the idea here is that each kind of element of this polynomial corresponds to a diffusion on the graph, and then the convolution just kind of aggregate the outcomes of these diffusions. Now, that's the representation of graph convolutions in the node domain. Alternatively, you can also represent convolutions in the frequency or graph spectral domain. And the reason I'm going into this is because all the analysis that we're going to carry out later depend on this. And I have a theorem here, but it shouldn't even be a theorem because it's a very simple result. It's just an eigenvalue decomposition. But what this result is saying is that if we project the output and the input of a graph convolution onto the eigenspace of the graph adjacency matrix, something that's called the graph-Fourier transform, we get the spectral or frequency representation of the graph convolution, and we see that it is given by an expression that only depends on the coefficient of the convolution and on the eigenvalues or frequencies of the graph adjacency matrix. Okay. So since we want to show convergence of graph convolutions to graph-on convolutions, let me go ahead and define, give you a more formal definition of graphons. So the mathematical definition of graphons is that they're bounded symmetric measurable functions, mapping points from the unit square to the unit interval. But the easiest way to think of a graphon is as a weighted symmetric graph with an uncountable number of nodes. And here, we're mainly interested in two theoretical interpretations of graphons. The first one being as a limit of sequence of graphs, in the sense that the certain structures or densities of structures in these graphs converge to the same densities on graphons. And on their interpretation as generative models for graph families that can be obtained by sampling edges Bernoulli with probability given by evaluating the graphon at pairs of points. And here I have a quick example of how you might interpret the graphon in these two ways. So if we look at this from left to right, the sequence of graphs, here we have stochastic block modeled graphs that we can think of as converging to this limit graphon. But alternatively, we can see the graphon as a random graph model or a generative model by sampling points from the unit interval and then sampling these graphs by essentially just sampling the edges Bernoulli at WUV. And now that we have graphons, how do we define graphon convolutions, right? So the answer to that is also very simple. So, you can simplistically think of the graphon as this matrix in infinite dimensions. When we have, these infinite, these limits of matrices, what we actually define instead of a matrix multiplication is an integral linear operator with kernel given by the graphon W, which here I'm denoting by this operator TW. And so we define graphon convolutions analogously to graph convolutions by just replacing the adjacency matrix by this linear operator and computing successive kind of applications of this operator and aggregating them at the output. And again, same as graph convolutions, graphon convolutions also admit a representation in the graphon spectral or graphon frequency domain because these operators are self-adjoint Hilbert-Schmidt operators, and so they admit an eigendecomposition and they have a countable spectrum. And so we are also able to represent them in the spectral domain by taking projections of the output and input of the graph convolution onto the eigenbases of the graphon. And we see that much like the frequency response of the graph convolution, the frequency response of the graphon convolution only depends on the coefficients hk and on the graphon eigenvalues lambda. Okay, so before I go ahead and try to give you some of the intuition behind why convergence of graph convolutions to graphon convolution holds, I'll go ahead and tell you that this result holds. So this is what this theorem is saying. So what this theorem is saying is, if I have a sequence of graph signals or graph data converging to a graph-on signal or graph-on data, and if I have graph convolutions and graph-on convolutions generated by the same coefficients h of k, then the outputs of the graph convolutions converge to the output of the graph-on convolution. Now, what I haven't told you, and this is an important caveat of this result, is that this only holds if the frequency or spectral response of the graph convolution is a Lipschitz function. And this is not a minor restriction, because what this Lipschitz restriction means is that in order to have convergence, I need the variability of these filters to be restricted in some way. I can't have them very, very fast. Now, in practice, convergence is asymptotic convergence is a nice result, but in practice, what we're interested in is how can we use this result in practice, right? How can we use this result to learn graph neural networks for large-scale graphs? And this is where transferability comes in. And transferability is just the non-asymptotic statement of convergence, really, where here, instead of looking at what happens in the limit, I am looking at what happens on two graphs, say in the same sequence, converging to a graph-on with different number of nodes n and m. So again, yn and ym here are the outputs of the same GNN on two graphs of different sizes associated with the same graph-on. And essentially what the bound in this theorem is telling me is the error that I make when I take a GNN on on the graph, on the n-node graph, and I transfer it to the m-node graph. So this kind of like gives us an upper bound on the error that we would make if we were to train, for instance, the GNN on this n-node graph and transfer it to the m-node graph. And this is helpful because it agrees with the convergence, the asymptotic convergence result, of course, right? Because we can see that this bound decreases with both n and m, the size of both graphs. But more importantly, it really highlights this dependence on the Lipschitz constant of the filter, which is here written as AH, and it kind of shows us very clearly that if we increase the discriminability of the filter, of the sharpness of the filter, we increase this transferability error. And so we can clearly see that there's a transferability-discriminability trade-off that appears to make these two things incompatible in filters. So the discriminability, so actually I have a slide that will help with this. So what I mean by discriminability is, I have these two different eigenvectors here, right? So first of all, the green dots are the eigenvalues of the graph. The blue dots are the eigenvalues of the graph one, and these two things converge. So let's consider this as one eigenvalue, this is one eigenvalue. When I say discriminability, what I mean is my filter sharp enough to give different frequency responses or amplifications to these two eigenvalues so that I'm able to distinguish these spectral components? That was a great question because it actually takes us to the spectral domain, which is, yeah, go ahead. So this is another thing that I left out for now. So graph-on eigenvalues are contained, so the graph-on is a compact operator, right? The graph-on operator. So the eigenvalues are contained in the -1,1 interval. Yeah. This brings us to essentially the how we can explain this Lipschitz continuity restriction. So how do we go about proving convergence and transferability? So the first key fact that we have already seen is that in the frequency domain, graph and graph-on convolutions have the same spectral or frequency response, right? The only thing that changes is where it is instantiated at either the eigenvalues of the graph or the graph-on, but everything else is the same if the coefficients are the same. And the second key fact, which is also a good fact, is that, as I was saying, there's a nice result by Borgs and Chase and others that shows that when a sequence of graphs converges to a graph-on, the eigenvalues of the adjacency matrices of these graphs converge to the eigenvalues of the graph-on. So this is what we're seeing here when we look at the green graph eigenvalues and blue graph-on eigenvalues. So from these two key facts, we get a positive result, which is that at least in the spectral domain, we know that graph convolutions converge to graph-on convolutions. However, the complication comes in when we try to translate this result back to the null domain, right? Because we care about convergence and transferability in the null domain. And here the complication is associated with convergence of eigenvectors, which is not uniform for each one of these eigenvalues because the eigenvalue convergence itself is not uniform. And the reason why it's not uniform is because the graphon has this uncountable spectrum, but it's contained in this -1 interval and accumulates at 0. 0 is the only point of accumulation. And so what I mean by the convergence not being uniform is that as we start to look at these eigenvalues that are close to 0, essentially it takes larger and larger graphs for these eigenvalues to converge or to get close enough to the corresponding graph on eigenvalues. And so the complication here comes when we have filters that are sharp like this. What might happen is that this filter might give two different amplifications to graph and graph on eigenvalues corresponding to the same index, and this leads to larger and larger transferability errors, lower convergence, and so on. So this is where the Lipschitz continuity restriction comes in, because we can solve this problem if now instead of having sharp filters, we have filters that are flat or close to flat near 0. And then in that case, it doesn't matter if the graph and graph on eigenvalues are too far from one another, because all of the eigenvalues in this -CC interval here get more or less the same amplification. Now, I have talked a lot about graph convolutions and graphon convolutions. I haven't talked about graph neural networks. And like Alejandro said on Tuesday, there's a good reason for that. They're just minor variations of graph convolutions and graphon convolutions. They're just sequences of layers where each layer composes a graph convolution with a pointwise nonlinearity. But, and so, because there's such minor variations, we can expect, and rightfully so, that they inherit the transferability properties of graph convolutions. And this is what this theorem is saying. It's essentially the same theorem that I showed you before, with just an additional dependence on the number of layers L and the number of features F. And so, because this property is inherited, what we would also expect is that transferability, discriminability trade-off that we observe in graph convolutions would also be observed here. And it is. But it is actually, this is kind of where the nonlinearities kind of play an important role, because they alleviate this transferability, discriminability trade-off in graph neural networks. And the way in which they do that is essentially, at each layer, when you apply a nonlinearity, what happens is that the spectral components, in a given, in these different eigenvalues, they end up being scattered all around the spectrum, but in particular, some of these that are close to 0 end up being scattered to eigenvalues that are further away from 0. And these are regions where our filters can be more discriminative. They can have larger Lipschitz constant. And so when this happens, this means that the information contained in these spectral components can then be discriminated in the next layer of the GNN, which in a way allows us to have more discriminability for the same level of transferability and vice versa. And so, this is a hypothesis that we have for why graph neural networks are more are better at machine learning than just linear models in practice. And if I had a bit more time, I would show you this in here in this example. For now, I'm just going to say that this curve represents the transferability error, and we see that for GNNs, that transferability error is lower than for graph convolutions, and here. These all achieve similar performance, so this is kind of like an empirical manifestation of these results. But let me go move on to the second part of the talk, where I want to talk about an extension of transferability. And the motivation for this extension comes from the fact that transferability is an inherent property of any graph neural network. And it's a nice property, but in some applications it might not be enough. For example, there might be safety critical applications where you have a small error allowance, and so the graph on which you would need to train your neural network is still too large, and so you don't gain anything. So the solution that we came up with Juan to address this problem is to now leverage transferability in the training of graph neural networks. And how do we do that? We do that by essentially just increasing the graphs, by training the graph neural network on a sequence of graphs. So the algorithm goes more or less like this. So we start by subsampling an N0 node graph from our graphon or our large-scale graph. We train our neural network via backpropagation on these small graph for one epoch or for a fixed number of training steps. And then we subsample a larger graph with size N1 and repeat until convergence. And what are the convergence guarantees of this algorithm? So the convergence guarantees of this algorithm are given by this theorem here. And what this theorem is saying is that if we let this sequence go to infinity, right? If we keep increasing the graph, the algorithm converges in a finite number of training steps to an epsilon ball of the solution of the empirical risk minimization problem on the graphon. So actually, let me rephrase this. So when we're training the graph neural network, we're essentially solving the empirical risk minimization problem on graph of size n0, then graph of size n1, and so on. What this theorem is saying is that by using this algorithm, this learning by transference algorithm, we're able to converge to the solution of the empirical risk minimization on the graphon, or in practice of the very large graph. And but this theorem has a condition, and the condition is this condition here in the middle of the slide. And what this condition is essentially saying is that in order for convergence to hold, what we need to verify at every step, okay, is that at every step, the difference between the gradient on the graphon and on the graph has to be smaller than the norm of the gradient on the graphon. So that condition is actually, in practice, it holds because the graph neural network gradients converge due to transferability. It's not too hard to show that from transferability. But in practice, that condition translates into a condition on the rate of growth of the graphs, which has to be sufficiently large for that norm difference of the gradients to hold. And so what this means in practice is that by tuning the step size and the rate of growth, we can achieve convergence in practice with graph sequences that actually stop at a graph size that is, in practice, smaller than the size of the large target graph. And so this means that we can save some in computational complexity. And so just to conclude, let me show you two examples where we observed these gains in computational complexity. So one of them was that multi-agent system example. So here we're training a graph neural network to control a set of agents to flock by optimizing a control cost that is a weighting of velocity differences in collision penalties. And what I'm plotting here on the center is the cost of these GNNs for both GNNs that are trained on the large target graph with 100 agents. So these are the flat lines. We're just showing the final accuracy on the test set. And then these curves, they are the accuracy or the control cost on the test set for the learning by transference algorithm. And so what we can see from this graph, where the x-axis is the number of epochs, is that the learning by transference algorithm achieves the same cost using much less kind of epochs or full passes over the data. And if we look at this plot on the right, which essentially shows the time that you spend per epoch as a function of the number of nodes, you can contrast these two graphs, these two plots, to see that it would actually save a lot of time and obtain more or less the same performance. And as a final example, this is the same experiment, but now on citation networks, where the goal is to classify the nodes of the graph, which represent texts that we want to classify in different categories. So here the metric of performance is accuracy. And here we see again that by training with the learning by transference algorithm, we're very quickly able to get to the performance of backpropagation on the large scale graph. And this is the case both for GCN, which is a convolutional architecture, but also for GraphSage, which is not. And so this is interesting to see that in practice, this also seems to hold to architectures that are not convolutional. So this is my last slide. So, I also wanted to talk a little bit about the limitations and extensions of this work. As Alejandro already talked about on Tuesday, the graphon is a good model for limits of dense graphs, but it's not a very good model for sparser graphs, which are most real-world graphs, right? And so it's very important for us to consider the extensions of these results to other graph limits, for example, manifolds and other graph models inspired by the graphon, but that have some more sparsity. We can alternatively look at other convergence paradigms. So there's this theorem of this theory of local weak convergence that is actually very general and applies to graphs with bounded average degree, which seem to be the ones that are closest to real-world graphs. And I think another interesting direction, given those numerical results, is trying to look at convergence and transferability properties of other GNN architectures, in particular those that are already that have been designed to deal to try to tackle this problem of training on large graphs such as GraphSage, FastGCN, and so on. So that's all I had to say. Thank you very much.
Thank you, Luana. Do we have questions from the audience for Luana? Oops. Yes, John.
Thanks for the for the nice talk. I just have a question. Maybe it's it's a bit naive. Is there a sense where you could give some quantitative results on how these models on graphons do on, let's say, very concrete random graph families? For example, could this model be used to detect the parameter of, let's say, Erdos-Renyi? You change two parameters of the Erdos-Renyi, and then you ask the question, can you actually separate between the two families? Or just do you have some idea of how these models do on a very concrete kind of toy model?
So I haven't, we haven't run experiments on these random graph models, but I think, if you think of very simple models such as SBM and Erdos-Renyi, like they have, we know their spectra, right? And so I think what we can do is we can kind of infer how how GNNs would do in these types of graphs by kind of like calculating the spectra of these models. So for example, if you have an SBM graph, where the intra and intercommunity probabilities are very close, then the second eigenvalue is going to be very close to 0, right? And so you're going to have that case where you have an eigenvalue that is important for your task, but that is hard to discriminate because it's close to 0 and your filter has to be flat around there. And so if you have noise, this might be a difficult task. But it's a great question, and I think it's definitely an interesting direction to pursue.
Thank you. More questions from the audience?
Thanks for the great talk. So I have a question on the last part on the transference, where you use a sampling algorithm. So does the convergence result depend on what kinds of sampling you use? Yeah, can you comment on that? Thank you.
So those results hold for either sampling the unit interval on the grid or sampling uniformly at random. We haven't looked into like finer sampling schemes, kind of like depending on the information that you have on the graph, but that's also a great question. But yeah, on the grid or uniformly at random.
Thanks. So the original idea was to have like a joint Q&A for all the speakers, but I don't know if you prefer to do that or just like have a conversation over the coffee break, because it's like we are already a little late because we started late. Any suggestions? Okay, let's have the conversation over the coffee break. Thank all the speakers of the session. Yeah.
Hola, hola, hola. Okay. Hello, everyone. Thank you very much for being here with us today. Sorry for all the logistics problems we had with this session. Maybe you didn't see them, but there were many. So yeah, I'm really happy to be here chairing this session on AI education in Latin America. Actually, this session emerged like an idea in one of our discussions in the program committee that we wanted to have a moment to discuss a little bit about, well, what's the current state of AI education in our continent? What are the options there? Maybe here we have students, undergrad students, people that are thinking they want to do PhDs or something like that. So we gather a panel of researchers from different countries from Latin America. And the idea today is that they will be presenting every one of us will be giving a short introduction about the current state of education in their own country, what are the careers that you can follow there, opportunities, scholarships that maybe you can think about applying. Then we will have Aisha Alagib from Africa, who will comment us a really nice experience they had there on creating a master, an African master on artificial intelligence that is basically a Pan-African master. All students gathered together in one place. Researchers from all over the world go and teach there. And so maybe we can use that as inspiration also for continuing the discussions that once we started about creating a Latin American master of AI. And then, during all this time also, the floor will be open for questions. The idea is that this will be a fairly informal panel where you will have the chance to ask and also comment maybe on also the situation in other countries that are not represented here, okay? A disclaimer at the beginning, we are really sad that two of our speakers could not join us today, Nayat Sanchez-P, because she had an urgent matter to attend. So she will be replaced by Pablo Barceló from Chile, and Laura Alonso Alemani, who unfortunately yesterday in the party was jumping a lot and had a problem in the feet. Yes, so yeah, I'm a bit sad about that because gender is not really gender balanced panel for that reason, but I hope you understand. So okay. We will start then with José Eduardo Ochoa Luna from Peru. José Eduardo Ochoa Luna is a professor in the Department of Computer Science at the Universidad Católica de São Paulo, Arequipa, in Peru. He is the coordinator of the Artificial Intelligence Group and the coordinator of the recently created Master Program in Data Science. So I will just share one slide for him to use. Oops, there we are. This one, yes.
Can you hear me? Good morning, everyone. So, I want to present part of the educational system on artificial intelligence in Peru. We teach artificial intelligence mostly in undergraduate programs in computer science. Unfortunately, we have a few computer science programs in Peru. I can mention Universidad Católica de São Paulo, UNCI in Arequipa, and Universidad Nacional de Ingeniería, and UTEC in Lima. We mostly have an umbrella program called System Engineering, but these programs are mostly information technology oriented. So in graduate programs levels, we have a lot of programs, masters, but unfortunately, mostly of them are partial time programs. We have a few full-time programs. I can mention the Computer Science Master Program of Universidad Católica São Paulo, San Agustin University, and the doctorate program in engineering which is offered by Pontificia Universidad Católica del Perú in Lima. And this same institution, these full-time programs, usually offer scholarships. And also we have a Peruvian program called Beca Presidente de la República, which allows us to send students to study abroad. We have two well-established groups in artificial intelligence. one at Universidad Católica San Pablo in Arequipa and another at Pontificia Universidad Católica del Perú. And we usually export students abroad. It's difficult to us later to attract these people, so we have a severe brain drain problem. Okay, that's all.
Thank you for this panorama of the situation in Peru. Then we'll continue with Sandra. Sandra. So Sandra Avila is an assistant professor at the University of Campinas, Unicamp in Brazil. She received a double degree in computer sciences from Pierre and Marie Curie University in France and from the Federal University of Minas Gerais, Brazil in 2013. So Sandra, I have your slides as well. So if you want to comment us a little bit on, yeah. There we are. Perfect. So you can do it like this. Yeah. Or I can if you want. Yeah, you can. Yeah.
Yeah. Okay, thank you, Enzo. Thank you, Khipu team, for having me again. And congrats, Khipu team, for this amazing week. We have to say that. All panel. So I have a hard task here to talk about the AI education in Brazil, and I should warn you that I will fail, because Brazil is so big, so it's impossible to talk about everything, and I'm sure that I don't know about everything. So it's a bias speak here, okay. So in Brazil, we have more than 150 public universities, and I add this number universities and faculties. So I show you we are big. And for computer science, we have more than 100 computer science programs, master and student. And this number is from 2020, okay? And I prepared this slide. Yeah. Enzo told me to prepare only 2 slides, and I didn't follow that. So it's my fault, okay? You can pass this slide. I can pass. Okay, and 3 years ago, the Federal University of Goiás created the first AI course for undergraduate students. So I think it's a big deal here. And in the same year, the Brazil, using the FAPESP Foundation, the FAPESP funding, created the first AI research center. I'm not sure if this center, it's really the first one, but I couldn't find other ones. And the next year, it's here, oops, yeah. And the next year, the FAPESP also created more than 6 AI research centers. And in those research centers, we have many opportunities for funding, for collaboration, not only collaboration in the same state, in the same city, but for Latin America especially, and different countries, okay? So it's a big opportunity. And one of the centers are in the University of Campinas, and I'm from University of Campinas, so I had to say that. And the Institute of Computing, the red point on the top, is one of the collaborators. And our lab, I think it's the next slide. And our lab, the Record AI Artificial Intelligence Lab, collaborate, of course, with the centers. We are 8 professors. I have to show the numbers. 4 research, 12 postdoc, and many students. It's better, yeah? No. Oh, I have one more slide in the beautiful one. Oh.
We'll go back. Takes time.
Okay. Two slides.
Okay.
My students from Record, they are here, and now Oh no, I have more slides. But it's good for the discussion, okay? This is one of the center, the Brazil Institute of Data Science. And the Brazil Institute of Data Science, especially for students, because we have DeepMind scholarships for this AI research center. We are more than 120 research. And now the next slide. So in 2021 and 2022, we have free scholarship for master students, and this year we have 1 scholarship for PhD and 5 scholarships for master students. And I think next year, because we will discuss next week on Tuesday, more scholarships for the students. And the most important for these scholarships is that the candidate should be a woman, low-income people, or who identify as black people. So it's an inclusion scholarship for AI. And the last one. That's the last one. So we are talking about education of AI in Brazil. And we think this is very important not to tell only in the university, but tell for the society. So we have a project, the name in English is Super Science Girls, and we talk about science, but the last year we talk a lot about artificial intelligence. That's it.
Great, and I think you mentioned 2 really interesting points there. I mean, among others, but there are 2 that I really feel identify. One of them is when you were talking about the creation of new undergrad AI. I think this is something we can also go back at some point in the panel. I think different countries in Latin America are creating undergrad careers to just from the beginning know that you are going to study AI. So it's not that you go through the typical CS or math and then you end up on that. There are like from the beginning undergrad careers, and these may have advantages and disadvantages. We can discuss that. And then you mentioned the DeepMind scholarship. I think this is something really interesting also because it's an example of how the private sector, and I think we will go back to that point also in our discussion, how the private sector can actually help the educational system, right? And not only sometimes, take students from there or professors. So yeah, thank you very much for that. Our next speaker will be Pablo Barceló, who, as I was saying, joined us just 5 minutes ago because Nayat, so thank you, Pablo, for doing that. Pablo is a full professor at Pontificia Universidad Católica de Chile, where he also acts as director of the Institute for Mathematical and Computational Engineering. He holds a PhD in computer science from University of Toronto, Canada, and he is a principal researcher at both the Millennium Institute for Foundational Research on Data and the National Center for Artificial Intelligence. Pablo, thank you very much.
Thanks, Enzo. Well, for obvious reasons, I'm not so well prepared about the whole educational system in Chile, right? But I think I have a more or less clear view of what is going on because I happen to be part of the creation of a new bachelor on data science 2 years ago that opened in my university, at the Catholic University, and then we had to study the landscape of what was going on, right? So the basic idea of this bachelor in data science was trying to precisely change a bit the way in which these things are traditionally studied in Chile. So people enter engineering through a common plan. They go there for 2 years. That's a traditional path, right? They go to a common plan for 2 years. And then they move to study computer science, and then they start specializing in, say, data science or artificial intelligence, right? And we believe that this was kind of a bottleneck because there were so many students that were interested in studying things related to data science or artificial intelligence, but that either couldn't make it to the engineering school because it's very competitive to get there, or they were simply not interested in following 6 years of study, right? And also we see, and I think that this is the crucial point, I mean, like, we are not training enough people, right? I mean, like, we need to train much more people in these areas, right? And opening this career was a way to try to do that. So we're trying to convince other universities as well, but it's a slow process, right? And another thing that I see as crucial is that we don't, in parallel to training people in these areas in in bachelors, we also need to train people from other areas in topics related to data science, programming, artificial intelligence, right? And I don't know if we are doing that properly or at the speed or at the pace that we need. Because these tools will become essential in say 5 or 10 years, and people from different areas should be learning them as well. Now, in terms of masters, there are several masters on data science, several masters on artificial intelligence. Most of them are professional masters, so are for people who have studied something related to this, and then they are working, and then and they want to become updated in these kind of topics. There are also academic masters. And there are several possibilities with fellowships. The government gives fellowships to these students. And also these centers that have started to appear in Chile, like the National Center on Artificial Intelligence or the Millennium Institute on Foundational Research on Data, or the Millennium Institute for Machine Learning Applications for Health. They finance a lot of students, right? So the possibilities are good. And many of our PhD students in these programs go abroad for at least one semester. There are funds from the university to do that, but I don't think we are exploring enough yet the possibility of exchanging students among our region. Yeah, I think that most of these students go to Europe or to the States, but you know, we are so close to each other. I mean, there are very strong groups here, and we should try to bring them together and have a stronger exchange programs. So related to that, I'm not aware of any exchange program here in Latin America that finances these things, and it would be interesting to explore that possibility.
Thank you very much, Pablo. I think this last point you touched is really important for like, yeah, strengthening the community of research also, right? Because education also touched research, and this is something also maybe we can comment after the round on what, or maybe if people in the public knows about programs that can be used for exchanges in Latin America, the whole, or in different parts like Mercosur or wherever. Of course, you are also invited to comment on that here. Okay, thank you, Pablo. So we now have Mauricio Velasco from Colombia. Mauricio received a PhD in mathematics from Cornell University in 2007. He became a Murray Assistant Professor at UC Berkeley and later worked in finance at Goldman Sachs International. In 2011, he joined the Department of Mathematics at Universidad de los Andes in Bogotá, where he is currently an Associate Professor. So thank you, Mauricio.
Thank you. Good morning, everyone. Can you hear me? Yes. Okay. So yeah, maybe the first thing is I would like to make a disclaimer that was made before, which is that I will give you an enormously biased view of the reality of IA in Colombia. So I'll basically speak about what I know, which is my city of Bogotá, and then I can tell you a little bit about the programs that exist there. So maybe historically, the approach to learning AI in Colombia was exactly the one that other people have described. So you go through a master's and maybe even a PhD in an area such as computer science or electrical engineering, and then you later on become a researcher in these ideas like AI. And I am not opposed to that track. I think that there are real merits of learning a lot of other things, being certain that whatever information you gain is something that allows you to generalize and change is much preferable than just learning a narrow set of techniques that allow you to work. But as has been said, this might not be enough. And so right now in Colombia, you can see that there's this effort to try to create new programs to integrate horizontally the alternatives that we have. So maybe the best example of this that I know is this thing called Sinfonía Unidades. Could we put their webpage? Yes, their website, that's right. So let's suppose that one of you is considering, Colombia is a nice country, why don't we go study there? Yes. So if that's happening, please do take a look at this webpage, Sinfonía Unidades, and you can take a look at the alternatives, the funding. Todavía no llegó. Okay. Do you want me to send you the link? No. Sinfonía Unidades. No, the standard, yeah. Yes. Oh, really? Sinfonía, how do you, so with a C, Sinfonía Unidades. Yeah. Yes, are you finding it? Yeah, exactly, that's right. Yeah, as I mentioned before, I'm kind of an outsider to this community, so what I did when asked to participate in this panel was writing to the people who really, so I wrote to the director of Sinfonía, Pablo Arbeláez, who's this Colombian, so their specialty is computer vision, and in particular computer vision applied to health, to the health sector. So Pablo was one of the speakers of one of these online things that were done for Khipu in between. There were 2 online sessions between the first and this Khipu, and he was one of the speakers there. So it's a really strong group. And as mentioned before, so they do have these DeepMind scholarships that are intended to foster diversity and things that the community finds desirable. Maybe one comment, there is another source of diversity that DeepMind supports. So it's not only for women and people of color, but also people who have low income, which in Colombia is a very significant source of challenges that are beyond how one looks. So I think it's a quite good initiative, but Paulo himself mentioned that while Sinfonía works closely with all the big AI companies, the only one that seems interested in funding education is DeepMind. And so this is an aspect that could be interesting. Yeah? So can we ask, or I mean, is there interest in the big companies that are gaining a lot from the AI revolution to try to step in, because there is not for altruistic reasons, but rather because there is a huge potential of like real talent in the region that is not being appreciated. And maybe just to create a controversial point and make this thing more interesting, I'm not so, I don't like very much this idea of brain drain. I don't think that the fact that somebody goes and studies at MIT is a loss for anybody. It's something that we want to, I mean, on the contrary, it allows us to create larger networks, and in the long term, I think that we gain more than what we lose from people that do these trajectories. But I mean, this we can discuss. That's right.
Yeah, I think many people may think that this is a controversial point. That's right. But yeah, I mean, for me, it's yeah, I don't know. We can discuss that, but I think it's really good because of the networks that you are saying.
That's right. Yeah.
But also at the same point, it's like if everyone leaves, and then what we do here, who teaches? That's important. But we have to create the conditions for people to want to stay here, right? And this is something, governments together with the private sector, and every one of us has to work on that. So yeah, it's a really interesting point. We can come back to that, also. Thank you very much, Mauricio, for commenting on the situation in Colombia. And then we have Marcelo Fiori from Uruguay. He received the PhD in 2015 from Universidad Nacional de la República. Universidad de la República, sorry, this is my bias, Argentinian bias. In Uruguay, from 2010 to 2015, he held different visiting positions at University of Minnesota and Duke University, and he is currently an assistant professor with the mathematics department of the engineering school at UDELAR in Uruguay.
Thank you, Enzo. So I don't have the same problem as Sandra because with the more than 150 public universities. This is the public university in Uruguay. And, but more than 80% of research is done in this university, so it's not that biased, my vision. So my vision will be on this school, the School of Engineering. There are other programs in other universities, in other private universities, but I think this 80% of research is the support that bias. So yeah, so the history maybe here in the School of Engineering is quite similar. We had, well, yesterday somebody commented on that while Alicia was receiving the distinction. There has been courses in pattern recognition for maybe 20 years or something like that. And then we created some other courses. Well, Pablo Sprechman visited us maybe 8 years ago, and he gave a short course on deep learning, and then we took that course and we made it like a course of the university. I think it's deep learning in computer vision or something like that. So we had a lot of courses, but we had like maybe 3 programs here at the School of Engineering: the mathematical engineering masters, the something like computer science masters, and electrical engineering, and we have maybe like a dozen of students every year. And then from I think 2018, we started with the same people that are around here in organizing Khipu. We started to think about creating a master's program in data science and machine learning, and that started in 2021 or 2021 in the middle of the pandemic, and that allowed us to go from maybe a dozen students within these three master programs combined to have more than 40 applications a year, and we had to select 20-25 students per year. But that was a huge step for the number of students involved in AI and machine learning. So maybe the majority of the old students, like myself and other students here that took that masters in electrical engineering or computer science, we were more focused on academia, and I think the new people that is doing now the masters in data science are maybe half and half, academia and more industry focused. We have some of the students here in the room. And yeah, and I don't know, for some of you maybe a little surprise, for some of you not at all, but the university here is free, and is public and free, and anyone can enter the school of engineering, for instance, and also the masters. So for the Argentinians, maybe this is not a huge surprise, but maybe for other countries there is. So yeah, these 40 or more than 40 applicants that we have every year in this master program, we have to select 20-25, but only for human resources reason, because we are only maybe 5-10 people here, the people you are seeing every day. And we cannot, I mean, we have 2021, 22, 23, we have already more than 60 students, and we are the same 10 people. So it doesn't scale. So that is a problem. And it's related to the problem of people going to work in other places. But fortunately, many of us I returned a long time ago, but many of the young people are trying to return to Uruguay because there's something that they don't find in Europe or in the US, and that is a good news for us, and that may be a way to tackle that, at least for now.
There is Khipu, basically. Well, thank you very much, Marce. Yeah, I think also something that is particular about Uruguay is what you were commenting, right, about the concentrate. Like, this is something different if you compare Brazil, of course, the size of the countries, but these changes of structure also, I mean, the educational systems are different. Everyone has, and I think this is really nice to see, like, the different perspectives, and that's why we put together this panel, I guess. So thank you, Marcelo, for that. And our last speaker for this part of the session is Diego Galeano from Paraguay. So Diego is a researcher in AI at the Faculty of Engineering, Universidad Nacional de Asunción in Paraguay. He received his PhD in computer sciences from Royal Holloway, University of London, and during his PhD, he also worked as a research fellow at Yale University and at Imperial College London. Diego, so.
Yeah, thank you, Enzo. Thank you for everyone who is also here in this discussion, because I think it's important for everyone in LATAM to have this type of discussion, which could be like a starting point for very good things, which actually already started with Khipu. Like, I never been here, I didn't know about Khipu. I don't know, someone posted on Twitter, and then that's how I became aware that Khipu existed. So I want to also make the disclaimer that this is going to be from my personal experience and what I know of. So as you know, Paraguay is a very small country. Most of the population is focused on the capital, which is Asunción. Well, we have 3 big cities actually now, but still most of the population is around the capital. And the largest university is also a public university, the National University where I work. So we have multiple faculties that they focus on different areas, probably similar to here as well, engineering, chemistry, and all these different areas of science. So in Paraguay actually happened something really interesting to me. Back in 2015, we had this standard curricula, like in the different, like, engineering or chemistry. We didn't have much of AI, although still, like, we know, like, in the world was already a thing. But the use of AI started actually in the industry before academia. And I think this happened because we didn't have critical mass of researchers who could teach, or people who were interested in teaching as well, because you may have people that are in the industry but they don't want to teach. So we had these few startups going around, doing things, processing data, building applications. So the government started this huge scholarship program back then that is called BECAL, Becas Don Carlos Antonio Lopez. And they were investing from 2015 millions of dollars to send people to the best 300 universities around the world. So all you needed was to apply to, if you wanted to go to Harvard, you apply to Harvard. If you get an acceptance letter, you tell the government, you know what, they accept me to Harvard. So they will pay you everything. Like, they give you the money, the stipend, like, you just go and this apply for masters and PhD. So this program is still running until now. So if you are Paraguayan, you can still apply. But what is interesting is what happened on these years is that people started coming back. And this means change, because they change the way they think. They have also a lot of interception with other cultures, which I think is also important, of mindset changing and broadening this understanding of what we can do with science, because, well, you probably don't know this, but there are a lot of poverty as well in Paraguay. Many people cannot go, like, in Europe or in the US for, like, holidays, or you don't have this usually cross-cultural interception, right?
So may I ask,
yeah.
is something known about the rate at which people return?
Which percentage of those will you return?
So I don't know exactly, but I think it's pretty high. And the reason is because in the contract you say that if they give you the scholarship, you have to be back for 5 years. So to contribute back something in the country. Yeah, it does make sense, right? Because the government is putting the money. And actually, I was part of that scholarship. So they pay me I think they cover over almost $150,000 for my scholarship. So which is quite an amount of money already. And they also helped me when I went to jail and all these. So it was pretty good, the program. Something I wanted to say is that because these people started coming, things started changing. Now we have more industry that is developing, and also in academia. We started working since I came back actually last year on the first AI master program in the Faculty of Engineering. So hopefully this will be coming up this year. And we are also applying for funding from an agency that is from the government. So hopefully it will be completely free for a student, and also the students will get money. So they will get stipends, so they don't have to work somewhere else to be in full-time in the master. So that's the idea, so that they can get the full understanding of these complex topics. There is a master that is also running from this year onwards in a private university, which is called the Universidad Comunera. You can, if you are interested on studying this and you want to go to Paraguay just to have a year of knowing a different country in Latin America, you can already go there. I don't know the tuition fees, but you need to pay, right? Because it's a private university. But it's pretty good, the program. I'm also teaching the recommender system, for instance. So, because I'm trying to help as much as I can to everybody, and I also agree that everything that is happening, from my point of view, is also good. Like people going abroad, they return, we have connections, you can collaborate then with other Paraguayans that are in Harvard, that are in Stanford, that are going everywhere, and then bringing back a lot. Actually, recently we had this director. He was director in a very big university in France, which I'm sorry, I don't remember the name. But he came back to Paraguay for 5 years to actually start moving the development of research groups, which was really good for the country. And yeah, that's all.
Thank you very much, Diego, for sharing this. Yeah, well, I'm Argentinian, so and I'm the Argentinian sitting here. I have to comment something about also our country. I guess there the situation. I mean, we also have public universities and private universities as well. Private universities here we have some graduated from there actually here sitting with us, and public universities are huge. They are free and open to everyone. You don't even need to give an exam to get in. You just start. Then you have to survive, but you have to just start. And yeah, yeah, like here. And this is something we are really proud of, I think, in Argentina. Also, there are scholarships available for Latin Americans as well. So if you are from any country and you want to do a PhD, well, you can be paid for doing that with us there in any of the different universities, private or public. So yeah, I mean, I don't want to speak a lot about the situation there, but it's mostly, I think, similar. Something that I'm seeing also is that like just 2 or 3 years, no, 2 years ago, I think some of the first undergrad careers on data science, we are calling them, or artificial intelligence, or at our university we are creating this year artificial intelligence engineering career. So this is happening in many countries, and I'm seeing the dates you are mentioning, and it's also only like everything is happening now. So this is really encouraging, I think, for us. But as someone commented before, there are not so many opportunities for exchanges within Latin America. We don't have an Erasmus program for Latin America, for example, or something like that. And that's why I want to invite now Aisha Alagib. Aisha, are you with us online?
Yes.
Perfect. So I'm going to bring Aisha into the screen. Just give me a second. Where am I? Here. There she is. So, up. Oh, wait, just give me a second. Okay. So Aisha holds 2 master degrees in mathematical sciences and machine intelligence from the African Institute for Mathematical Sciences, AIMS in Cameroon, and the African Master in Machine Intelligence in Rwanda. She's a research assistant at the German Center for Artificial Intelligence. And Aisha has been, well, all around the world, basically. She's been at Mila, Quebec also. And her passion for machine learning communities has led her to continue organizing deep learning in Indaba, for example, that is the equivalent to Khipu. Actually, Khipu got inspiration from Indaba at the beginning. So Aisha is one of the organizers, also women in machine learning at Data Science Khartoum, and recently she joined the Cohere for AI community. We invited Aisha today because we wanted to hear the experience from another continent on creating a master like the one Aisha attended and also was a TA there, that brings together all the African countries and maybe think about whether we can do something like that in Latin America. So Aisha, we are seeing you there and the screen. I don't know what time is there and where are you now, but welcome and the floor is yours.
Okay, can you hear me well?
Yes, we can hear you perfectly.
Thank you for inviting me. My name is Mia. I'm so excited to present my master and my experience. Yeah, I think you can see like one of my visitors there, one of my collaborators, also my lecturers are already there. So I will start. I'm going to introduce African Master of Machine Intelligence. But before that, I want to introduce first African Institute for Mathematical Science, where I did my first master. So African Institute for Mathematical Science is an African network that's focusing on bringing African students from all over the continent to study mathematical science for 1-year program. And then later they give opportunity for students to apply for PhD or for job, also give you like a chance to get interview one of the companies in Africa or over the world. And then from there, like get the idea of African Master in Machine Intelligence. So African Master in Machine Intelligence is also 1-year master program offered in partnership with Facebook and Google that was launched in Kigali October 2018. I was part of the first cohort there. So AMI tracks applicants from like undergrad students or postgraduate students who are having backgrounds in mathematics, statistics, physics, and computer science or engineering from across Africa, and then bring them together in one place to spend 1 year and learn about machine intelligence. Yeah, so thanks for our sponsor, who the master has been funded by Facebook and Google, where they cover the living cost for the students for 1 year. Also, they provided all the needs for studying, like computers, computation resources, and also travel funds for going for a conference and attending some school. The leadership of AMI has been started by Mustafa Sise, who was the head of Google Accra AI in Ghana. Thanks to Mustafa, who started this idea and will bring it back to Africa, and it was one of the first master of AI in Africa. Also, Tita has been the academic director of the master. The statistics of the program started from 2018. AMI has been started in one center of AIMS, which was in Rwanda, and then the next year has been 2 centers, were in Rwanda and Ghana, and then the 30 is moved to Senegal. So the acceptance rate is 60%, and for now, has been covering 23 countries in Africa. 47% of the students are female, and 91% from the students have been graduated successfully from the program. And the good thing is that a alumni from AMI, they get the chance to mentor students for AMI and give back to the program. I was also like part of this community. You get the chance as a mentor student or come back as a teaching assistant or working as a researcher with the student. Some of the lecturers we had 10 of them. This is just like some statistics from the websites, but we had like more lecturers from all over the world who they volunteer and come to the program for 2 or 3 weeks, or maybe less than that, depending on their availability, and then get the chance to interact with the students, spend all the day in classes, and then going out, learn about African culture, also visit the countries. So how is the program? What's structured? So the program is 10 months courses, and then followed by 3 to 5 month thesis. For the thesis, you have the choice. Either you stay in the AMI center to do your thesis, or you go back to your home country, or you also can have the choice to do it as maybe like as research in one of the Spencer Institute. So the program includes like when the student admitted to the program, maybe you don't have any backgrounds about programming or machine learning, but all you need some background about mathematics and maybe linear algebra. This can help you to understand the concept. So first thing in the program starts by programming bootcamp, which like most of the time is taught by one of the AMI organized students or maybe other volunteers from other university. And then followed by foundation of machine learning and deep learning. Here we will introduce like linear algebra or maybe like some optimization methods and other foundations. And then followed by computer visions, NLP courses, optimization, RL, geometric deep learning, kernel method. So the courses used to change over the years depending on the lecturer's availability. But most of the time, this is the basic thing used to cover every year. What after AMI? So when the student finish AMI, or let's say during AMI, you get the chance to meet one of the lecturer, and then also like have the chance to meet some of the recruiters from companies or from university, to just like have mock interview, learn about how you can proceed to your next level or next goal. So many of the students have been joining now, are like either working or interning in DeepMind, Hugging Face, Mila, Google, Facebook, and Facultad Institute. Also, like people some of the students choose to go for academics, and then you have like students now doing master or PhD at UCL, Stanford, University of Montevideo, and other universities. I'll just give sample of some of the information. So just want to share my experience as students. Got the chance to do my first master at AIMS, and then from there I got introduced to AMI and applied, and then got accepted. So when I joined AMI, I didn't have any backgrounds in machine learning, but I had backgrounds in mathematics and computer science. So through that year, I got the chance to do my first project in machine learning. I explored like different research areas, and also like I had the chance to join like machine learning computation, and I remember many of them, like I did computation for Cassava, and also like some of ICLR computation. Also, it was a great opportunity for me to like introduce to one of the machine learning communities. There's some communities in Africa or outside Africa. For example, like I got the chance to introduce to deep learning in Daba. And getting back to my country, we used to like each year like organize something called Indaba X, which is more chapter than Indaba, to like bring the students from Sudan, to introduce them to AI, and then show them like what opportunity they can get in the future. Also like collaborate with other people. Also like I was happy last few months to join international communities like Cohere for AI. Also, like during AMI, we got the chance to like attend a conference and like create networks and then collaborate with others. I got the chance to visit Victor Institute while at AMI, and also like visiting Mila as intern. And so I am like now I'm working as research assistant in the FKI German Research Center. Yeah, thank you so much. Just giving some links for feedback. That's just sharing my experience. And, thank you.
Thank you very much, Aisha. I think it's amazing what you made there in Africa. And it can be really maybe an inspiration for creating something like that here. So after this round of presentations and Aisha's talk, I wanted to open the floor for questions from the audience. I have some topics that we can discuss, but maybe it's interesting to hear if you have comments, questions, or something to share with us now. Is anyone? Randall here and Rodrigo there. The microphone is coming, yeah.
Yes, first. No, I wanted to say that there exists something called Grupo de Montevideo, Asociación de Universidades Grupo Montevideo, that groups many universities, public universities only, but in Uruguay, Argentina, Paraguay, Bolivia and Chile, I think, in Brazil. And it has a program for exchange students. So this can be used. And also, we can create a sort of chapter inside the group of Montevideo, specifically in data science. It's something that maybe we can think about. And there are funds that, if we have that group, that permit the exchange of professors, students, between the universities that participate on that. That's one thing. And the other thing is that maybe I listen that there is DeepMind becas or scholarships in Brazil and Colombia at least, and maybe in other places. And well, I was thinking that maybe we can think of a DeepMind supported program specifically for the exchange between our groups. Most of us are doing big efforts locally to develop, well, has it done, has been said, but and in general, our students want to go abroad, and it's very good, but to go to the north. And it could be, I think, really very important if we can create a program, even a small one. Maybe if we can begin with, I don't know, 10 exchange between all the countries we have is not too much, one for each country or something, in which somebody who is doing the PhD or the master in their university can pass one semester or 1 year in another country, in another lab. I think if we do that, this is not as ambitious as the African experience. I think it's a good idea to go to that a master degree or something, but this is a more a first step, I think, that will permit at least two things, I think. One is to create real links between us, because these students are the vectors of cooperation, and it's like that works. And if one of these students have two thesis directors, one of each country, this will create really, I think, important communication between us, much between Khipus, you know, and also for cultural reasons. No? So I think we can think about a program like the African experience. We tried in the past and we failed because we don't have really the resources. But, and also maybe because cultural reasons, but I think was mostly because the resources in that time. I was part of that discussion. But we can also maybe discuss this other way. In this other way, we have public funding. For example, Grupo Montevideo is one of these. We have public funding from each country, so it can, the people who, the committee that work in this exchange program can talk maybe with the agencies of each country to have one from each country, and we can maybe create a sort of pool, and maybe we can have support from something like DeepMind or wherever in order to support this exchange. And I think if we do that, this will be the beginning of something.
Yeah, thanks. Yeah, I think it's an interesting, really interesting idea, and we have to take notes of this. What I like particularly about the African Master is also that researchers from around the world go and teach there. So how to mimic this experience in this program is difficult, but we can definitely think about that, I guess. There was another question there.
Yeah, so one of the problems that several people mentioned is that if you want to have programs, you need faculty, so you need people to teach. And in recent years, the pay gap problem has increased substantially. So now that you can work remotely for a company abroad, it's pretty hard to keep people in academia and teaching. So I'd like to know if in other countries you had developed strategies for that, so programs for faculty. So how do we keep people teaching, and I don't know, are there programs to have like a differentiated salary for this topic in particular, or I don't know, mixed solutions with the industry? So if you can tell us about that, that'd be great.
Someone wants to answer that question because I'm Argentinian, I'm not gonna tell him nothing new. I don't know if there are experiences in some of your countries where there are like joint positions between faculty and industry. Doesn't exist. Okay. I think it happens abroad. I have seen like many of the researchers who are actually giving talks here have like this joint appointment. So this is maybe a strategy for difficult to implement, I guess, because this doesn't depend on us. It's mostly academic politics or something like that. But yeah, so no experiences abroad.
Hello, I have a comment about that. We are struggling with that situation. We are from Argentina, so yeah, it's being quite dramatic. We are seeing, for instance, that in our bachelor's degrees in software, we are seeing a spike in the numbers of the students that are willing to take those courses, and we don't have enough people to teach there. We did an experiment, actually, trying to improve that. So we asked the companies with, that have people interested in at least being teaching assistants, you know, to help us, because essentially we are creating the workforce that they will use afterwards. Use, that's the word. So the experiment was quite simple. We asked them, what if you pay them to teach in terms of like, all right, if you have to log hours and you are teaching, that's totally fine. We will cover that part. And that helped to a certain extent. But the problem is that we cannot push the industry, every single company, you know, to follow that example. We did the experiment with Globant, but we couldn't reach other companies. So I guess it's like a more like a question, I guess, that we should start thinking about the way in which we can approach industry to collaborate with us in this sense. Of course, we are making a lot of mistakes in academia to solve these kind of issues, but at least we can ask for help to them. And with these tiny little things, we managed to get, I don't know, like 10 or 15 new teaching assistants. And that was really helpful, especially when you have like 600 students or something like that. So I was wondering if we can at some point come up with these kind of solutions.
No, that's definitely an interesting approach, I guess. I don't know if someone wants to comment on that. Yeah, Sandra, go ahead.
I remember that we have a good experience in the Institute of Computing at the University of Campinas in pandemic, because the students almost then need to work to help their family. And the institute asked the company, the colleague just said that, to make donations. We just ask. They need trained people, and we need people to do research. And they start to make donations, and now every student that we have at Institute of Computing, if they want, we have scholarship for everyone. So, and most of that is because we are receiving donation from companies. And we can increase, the donation, the scholarship from the public funding, and we start to increasing the scholarship with the donations of the company. So we can pay more for the students. That's a good option.
Yeah, that's a solution for students. So for teachers and for students. Yeah, no, that's interesting. Yeah, Diego?
So I just wanted to add from my experience something that I've seen in Paraguay happening, but more in the private universities, is that since the pandemic, everybody moved online basically all over the world. So what they do is with this new master program, they do most of them online. So therefore they don't have problem with the amount of students basically, because you just need a premium Zoom account and then yeah, you can get as many students as you want. So that's I guess one solution that's how they are facing this problem, because actually it's a problem as well there, right?
I don't know, Aisha, do you have any comment on the African situation, for example, for what we were discussing here about whether professors are allowed to have joint positions, or how is the situation there? Can you comment something on that?
Yeah, so one of the professors, they were coming from abroad, and also we had some African professors. So I think there's some flexibility. I remember in my first master in African Institute for Mathematical Science, where some professors who work in industry and in Cameroon, I remember. But the thing is that you give a chance for students to do research for them in industry, and then at the same time to give them a chance to teach in the master.
Mm-hmm.
So it was more like you give back to them. So.
I see. Cool. Any other here, yes.
Hi. I know the panel is most focused on tertiary education, but I wanted to ask if maybe some of you can share your thoughts about introducing basic AI concepts in secondary or primary education. I'm aware of some initiatives in Latin America and abroad from different points of view, maybe some trying to abort technical things or from a digital citizenship point of view, but I wanted to know if some of you think it's actually necessary to do that. There are particular things about AI that should be introduced there, or?
Yeah, I think so. I think that more than AI or particular topics, what we should be introducing in schools is computational thinking, right? And this we have tried to introduce in the Chilean curricula for many, many years, and it's very difficult because but not knowing computational thinking is like not knowing English, right? Or it's like, I mean, it's an essential tool, and but you have to do a political job to convince, you know, the ministry and then the teachers and so on to bring this into the curricula. It's not so easy, but I think it's essential. I don't know if in any other country you have tried to do that and you have succeeded.
In your way, you mean? Yeah.
But then you need teachers also.
Yeah.
More teachers, because you need primary and secondary level teachers all over the country. Maybe that's something you could say about
Germán.
I agree, we're still trying. I think we need more human resources or train the teachers. It's quite difficult, as you said.
Yeah. Yeah, in Argentina, I know there are some initiatives from Fundación Sadowski, I think, yeah, who are working with Ceval. But yeah, I totally agree, and it's fantastic that every time you talk with the students about these topics, they get really interested. So it's like just a matter of going there and doing it. Because I remember 1 or 2 months ago, I gave a presentation for a book that we wrote for high school, like students in high school, about AI. That you can download, by the way, and the students were like, when I started to talk about AI and ask questions and they were answering, it was fantastic, like the interaction, and it was like, I don't know, 10 years old students, they were not even high school. So yeah, we just need to do that. But human resources, again, I guess it's one of the problems, right?
But the school students have an amazing capacity to do self-learning of this kind of topics. So it's perhaps also a matter of offering the right material and motivate them. Yeah? But it's very difficult.
If I can ask another thing. This is like a third direction, like the training for us, for academic people or people who are going to work in the industry, then small children or people in education. And when we started this master program, we had a huge demand from a third public, which was like people in communication, media, journalists, psychologists, medical doctors, yeah. So like an alphabetization program that is necessary. Of course, not the same. They don't need to know how to compute the gradient of a quadratic function or no optimization, but they should. But they have to know how to interpret things, because we see every day headlines in newspapers which they don't necessarily are completely true.
Totally. So there was one question here, yeah. And another, there is one there and then here, yeah.
Yeah, hello, Steffen Hartel from Chile, University of Chile. And I've been pretty much active in the field of medical informatics, and this is also a young discipline, and in Latin America for about 15 years, but artificial intelligence is even younger, no? You're still a really baby. So when we think about really introducing artificial intelligence into our curriculum, as I heard, it's really a tough task, no? And from the discussion so far, I heard topics, I heard skills, and I know that there are many intelligent people walking around. They know which course to grab in order to grow, no? So there's a lot of confidence in that. But is there something like a competency matrix or something in the field of artificial intelligence already really expressed in competencies which the educators and the information could really take and transform into courses to measure? If I am in a university now and say, okay, how do I cover the field of competencies in artificial intelligence? Could we measure that already, or is it still too young to have like a benchmark or a number which is coming out, or light, and I'm doing bad, I'm doing middle, I'm doing good? Is there something established already in that direction in artificial intelligence?
Does anyone wants to, Mauricio, you want to comment?
Yeah, I would like to maybe say something. There is a question one has to ask maybe before the one that we were asked, which is why do we want IA education? I mean, there are several objectives that are very different. I mean, somebody who intends to do research in AI, somebody who intends to work applying the capabilities of AI, somebody who wants to do like public awareness of AI, like Marcelo just explained, and like each of these many realities of what AI will be for in society are completely different and require completely different set of skills, specific knowledges, and even more competencies. So I think that the key point is that we need to do education at many levels and with many objectives, and so maybe we need to think also about the different fronts in which this could be extended. Because I feel that it's somehow very monolithic, yeah. So like, even if you look at something like the African Master's Program, it's something that is very specific. Somebody that does this and then can go work in the industry tomorrow, can implement a transformer in 5 hours, yeah, and that's, or I don't know, 2 minutes. Yeah. And this is very cool, but it's somewhat narrow. I mean, maybe for somebody who wants to explain what AI means for society, which is a huge problem, maybe these are not the skills you want. Maybe you want somebody who does philosophy instead. It's a...
Yeah, no, totally. I think it depends. I guess the question was going towards more the kind of standard curricula for AI, like if you go for like maths, right? Like maths, it's a really old discipline, and it has kind of a curricula or more than that, competencies that I know it's not the same. So yeah, no, we just created this, for example, new engineering career in AI, and these are things we were discussing, but basically, yeah, we established the curriculum, we discussed what is this person gonna be doing in society, and we defined some, but it's just one initiative. Like, I think now that many are going around the world, like many centers, educational centers are creating careers like that, these kind of things may start to emerge. Yeah. Yeah, we are almost, like, we have to, like, 5 minutes more if you want, and then, yeah, we can close. Yeah, sorry, Marcelo.
No, just a quick comment. Here in the master program, we have like 5 areas. So students, they need to do 1 course in each area. It's something like in the middle. There are no like mandatory courses, but they have to do 1 course in statistics, or 1 course in machine learning, 1 course in data management or something like that, and we're trying it. We don't know if it fits the needs, but that is what we are trying now, and it's a 2-year program now. So let's see.
Yeah. Hello. In Brazil, we don't have a national program to introduce AI or program in schools, but some universities are doing a work like Federal Fluminense University, where I work, and we have some programs for computer science and programming, basic concepts in programming in public schools. And in my group, the Ethical Intellectual AI group, we are developing a literacy course to public schools and to different levels. We are separating this in modules. The first, the concepts of programming. The second, what is AI and what's not AI. And the third module is about ethics, to develop a critical way to be aware of the technology in their lives. In some point, we'll be aware we need to work with the professors from the public schools too, and it's harder. And it's my experience, and I would like to hear from you if AI ethics issues have been introduced by your students, and how.
Anyone wants to answer that? Ethical, like, you mean in the careers, in the curriculum, right? If ethics, it's in the curriculum of these programs, yes. Yes, in our case it is, I don't know.
In the case of the Bachelor on Data Science that we built in the Catholic University, there is a special course called Ethics for Data Science, in which the students learn ethics not through reading Aristotle, but understanding the real problems and then trying to see the ethical dilemmas behind it and how to solve them. Yes.
So in the center, Sinfonia, that I was mentioned, the purpose of the center, or one of the stated objectives, is to review any kind of master's program or even undergraduate or graduate program that intends to teach AI, to guarantee that components such as the ethical component are done to levels that are satisfactory and reasonable. So there are even like guardrails in place to prevent the existence of programs without the component that you described. So this is very well understood as a necessity.
Okay, well, it's already 12, so I don't know if there is any last question there. Saul?
Hello. Thank you. Well, it's a quick, you could say, comment and question. Maybe to describe a little bit how we have tried to address in Costa Rica this problem of retaining talent and develop talent for teachers and or professors and researchers. We have in our universities, each one of the public universities have a public, you could say like a private public foundation that it's able to get funding from the private sector for either both research and teaching. Actually, we have a data science program that I described briefly in my presentation. And it's been, I think, quite successful because we have had a very good reception from the industry. And well, it's also been an opportunity to offer like a way to address this salary gap that researchers and professors have. However, I think I'm a little bit skeptic still about this mechanism because for doing research is a more mid-term and long-term investment. And for doing that, we rely mainly on public funding. And well, that's pretty much taxes. And well, we have been discussing that perhaps, well, for instance, in Costa Rica, the software industry is quite developed and very well established. One of the ideas that we have discussed among our peers is that perhaps maybe we can propose to the software developers and software exporting companies that maybe we can come up with a tax, like a specific purpose tax that it's able to fund research in general, because they benefit from that. I mean, Costa Rica is a well-known place for US-based companies that come and do investments. And I think that we have to make the discussion. I don't think that taxes is a bad word by itself. I think it's a problem of how we use the taxes. We can develop different kinds of metrics to really show them that we can give back what people are investing, right? So, I don't know, I think that perhaps we have to think about it in general. And I would like to know what's your take on this. I don't know if you have any kind of discussions about it in your countries or universities.
In the case of Argentina, the software law has tax incentives, for example, for companies doing research. So in that sense, I don't know how many are really taking advantage of that, but there is that. But yeah, I don't know the situations in other countries or whether, yeah. No. Yeah, go ahead.
In Brazil, we already have the same, I think, incentive by law. So, and that's why the company gives
well, that's good.
donations for us.
Yeah. Yeah, okay. The problem is that sometimes companies say that things they are doing is research and it's not really research and they get anyways these incentives, but this is research. This is giving money to, yeah. Okay, interestingly. Okay, I don't know if there is any final comment. Otherwise, I would like to thank a lot Aisha for sharing her experience with us and all the members of the panel and you for being here. And yes, we will now be having lunch and then going to the Solis Theater at 1? Yes, from here, right? We don't have, there is? Okay, I'm supposed to be the one. But yeah, the buses are going to leave from here, so we are on time and you can have lunch. Thanks. Thank you, Aisha.
Thank you.
Ay, yo estoy meta a mover esto. Thank you very much.
you.